The last part of the tutorial about implementing a functional language in Scala. In the previous parts, we implemented expression types, parsing, De Bruijn indices, evaluation, and type checking. In principle, that is sufficient to work with the language. We can work directly with its expression types as case classes. We can convert them into final evaluated expressions, pretty-print them. In principle, we have implemented the entire language as an interpreter. Another thing we can do, which we will do in this tutorial, is to implement a sort of a compiler from that language into Scala. Now, it is going to be a very high-level compiler. It's going to create Scala values that compute µDhall expressions. And these Scala values aren't going to be interpreting µDhall expression trees. They're going to be compiled in some way, but in a high level manner, meaning that we're not going to manipulate bytecode or Java bytecode. We're not going to create any kind of code for a virtual machine, which a compiler might want to do in order to do optimization, for example. We're just going to do a very simple kind of a evaluating compiler where there will be a speed up, but the speed up is certainly somewhat small. However, the main convenience here is that we can convert µDhall expressions into Scala expressions that are compiled normally as Scala expressions are compiled. So let me explain how that works. The first thing we will do is we will convert Dhall expressions into type tags. So I'm going to use the library which is called µReflect, and that's a small library that creates type tags. Now the type tags are representations of Scala types, and these representations can be examined at runtime. So that is a kind of a replacement for type tags. It has more power and more flexibility than type tags. So the first function we're going to implement is asTag, and now asTag converts a µDhall expression into a tag for the type of that expression. In other words, the expression needs to be a type. It needs to be already in the beta normalized form, so we're not going to do lambdas or applied, so it has to be a type. So for example, natural or function from natural to natural. So if this expression is a µDhall type, then we're going to produce the corresponding tag of that type in Scala, if possible. And if not, then we produce an error. That's the point of this function. And actually, we only have three cases. First, we have a for all. So that's a type, which is a function from this to this. So we convert this type to a tag, this type to a tag, if possible. If not, we're going to fail in this for yield. And then we do this application, which is a µReflect function that creates a function tag. So it's going to be a type of function 1 with 2 parameters, which are tags. So this is functionality that the library provides. So in this way, I have implemented types of all functions that have types represented in tags. And what are those types? There are only two, natural and type. So for type, I don't know what to use for Scala, because natural, well, I can define what natural means. It's just integer. I think I defined it somewhere. In in this notebook. But what do we do for the type itself? So there isn't anything similar in Scala. So we're just going to use nothing as a special value. So here are some tests. So if we have a Dhall, µDhall expression like this, so that becomes a Scala tag for the Scala function of this type signature. And you see it's correct. So if you have a higher order function in µDhall is written like this, and in Scala, this is the actual Scala, native Scala tag for this native Scala type, and that is being tested, that we can create this. So because in this very simple language, µDhall, we are only going to have functions with natural numbers. Pretty much you can have natural numbers, or you can have type parameters, and there's not much else you can have. So we will have these tags, and then type will be just tag nothing, and we can represent types of functions in this way. Now, the more interesting part is how are we going to translate expressions into Scala. So for example, a Dhall expression, which is maybe some lambda or maybe not a lambda. How are we going to represent that in Scala? So to do that, I need to explain. So what we're going to do is we're going to translate into Scala individual sub-expressions. Of course, we're going to do just recursive function that takes a sub-expression and translate that into Scala. But what if the sub-expression has free variables? How do you translate that into Scala? Well, you can't directly. So actually what must happen is that we need to keep the evaluation context. That is, there are some variables that will be assigned later, and we must use some of these variables and compute something with them. And so to represent that structure, I'm going to have essentially a function from a variable assignment to any. Now I'm just going to use any here because types will be checked separately. Now, what does it mean? So this variable assignment, so closure v is a case class that will be the result of converting µDhall to Scala. So any µDhall expression converted to Scala will be this closure v. And when we want to get value out of it, then we call this method closed value, which assumes that there aren't any free variables and that we can actually get the value out of this. And so we pass an empty map, empty variable assignment to this function, and we should get a result because closed expression can be evaluated with no extra free variables. So our goal now is to convert µDhall expressions into this type closure v. And then you see I use closure v here as a type of the variable assignment, and this variable could have De Bruijn indices. So I'm just keeping as much µDhall there as possible. So we have pure closure, which is a function that already knows what to return and doesn't need any variable assignments. Now, here I have a source. This is mostly for debugging purposes. So I can print this closure expression, and I can see from which Dhall expression this came. But for evaluation, we won't need this. So, and also, again, for convenience, I'm going to have a special class here, function v, which is, in some sense, it's a verbose function. It's a function that was converted from µDhall, but it knows its source code. It can print the Dhall expression from which it was converted. And so I'm going to use those when I convert Dhall functions. Again, this is just for debugging purposes. It's nice that you know that your function was made from a specific Dhall source code. You can check that everything is right. But this is just debugging information. So this class is just a function, any to any, with an extra Dhall, µDhall expression that is kept here for debugging purposes. It's printed. I'm going to implement this function as Scala. So this is going to be a function that takes an expression. It implicitly takes a tag, and the type parameter will be checked. So how are we going to do that? So first of all, we're going to infer type of this expression, and we get the tag that corresponds to this inferred type, and then we check if this tag the same as what was given here. So we will write code like Dhall expression dot as Scala, and then in the brackets the type that we expect that expression to have, and if that type doesn't match, then there will be an error. Otherwise, we will have an actual Scala expression. So so we do this. If the tag is correct, then we continue. Otherwise, we have an error. Then we convert value to Scala. So this is a function that we will implement, which will give us a closure v. We get the closed value, and we cast that as a. So on error, we throw exceptions. So that's kind of a high-level interface that checks types and so on. And the low-level interface won't check any types, and it will just convert an expression to a closure v. So so what is going to be the idea? The idea is that we need to walk the structure of this expression e. But this walking, this recursive procedure, is going to be outside of the result that we're returning. So we perform the analysis of this expression, and then we return a value which will be building up, which will be this closure v. So that the closure v will contain some Scala code, some functions maybe, but it will not have to pattern match on the Dhall expression anymore. It will already have done this before creating this closure v. So in this way, it's kind of a compilation. It's not interpretation anymore. But of course, it's a compilation only in some high-level sense. So let me show how that works. So first of all, closure v needs a value of this type. It's a function from variable assignments to a result. So let's create that function. What that function is going to be, we need to match on the expression. So now we are matching. We have not yet returned the function. We have not yet taken, this argument. First we match, and then we return a function. So the function is returned as a result of matching. So the matching is outside of that function. So if there's a natural literal value, very easy. We return a function that ignores the variable assignments and just returns that value. Then if it's a value, it's a variable, then okay, well, this variable must come from the variable assignment. So now we can return a function that takes the variable assignment, finds if that variable has that assignment, and if so, we have the variable assignment, which is going to be of type closure v again, so we have to apply its Scala v method again on this Scala vars for any further variable assignments that might be necessary. Otherwise, we throw an exception. So how do we process a lambda? So we need to return a function that takes variable assignments and returns a function corresponding to this lambda. So suppose, for example, suppose we have this sort of µDhall code. It evaluates to this, but our Scala compiler is not going to evaluate this symbolically. It's going to compile this into a Scala function that takes a value of type any, cast this as big as integer or big int or whatever. In my implementation, actually it's called natural. It's a type alias, but anyway. So then it adds this and takes this function and applies that to the value 2. So this is supposed to be the Scala code that we will now create, because we're not going to actually evaluate any of this. We're just going to compile, and the Scala will evaluate later. That's the idea. So the body is the function body. So we convert that body to Scala. The result is a function of variable assignments still. So now we can create the function that we need to return. We shift the variables because that needs to be done. Obviously, we need to shift the variables inside. And then we return a function from this x to the body that takes all the variables that were before except shifted, and then this extra assignment variable 1. This extra assignment of name to the var x that we got here. And with these variable assignments, we return the function body. So this function body has access to the x as the name, and it also has access to all the variable assignments in the outer scope. So in this way, we return the correct lambda. So for all is just a function type, and we return the tag for it. Let is evaluated like this. So let name equals subst in body is the same as this lambda application, because then it just substitutes subst into name into body. So we have a function that does this, that converts let expression into applied expression, and we're just using that and converting value to Scala. Annotated, we skip the type annotation, convert just the body. Applied, so we have a function and an argument, we convert value to Scala, and then we return a function that applies the function to its argument. So again, I want to emphasize, so all this convert value to Scala, which involves parsing, walking down the expression tree, this happens outside of the function that we are returning. So we are returning a function that already has the results of all this parsing and conversion. In this sense, I mean, it's kind of a high-level compilation. So this is Scala code that will be compiled, but it no longer has to walk through the µDhall expression. And finally, the built-ins. So we need to define how they are implemented. These are going to be Scala functions that we actually return, implemented in Scala code. So built-in µDhall functions are mapped into Scala functions that we're going to implement in a second. Binary operations. So I'm going to make this helper function here, because then it's easy to add any further operations if we want to. So we convert to Scala left, convert to Scala right, and use op returns a function of Scala vars. Now, this is actually not right, because it takes the argument Scala vars before it parses the function. So this is actually not what we wanted to do. We wanted to do this. This is what we wanted to do. In this case, we have the correct results. So now we have to implement these native functions, as I said. So this is just subtraction. This is a loop that applies a function, given function, to argument many times. So that's actually it. So then we can compile things to Scala, and let's test. So these are numbers and various expressions that evaluate two numbers. Now these evaluations are done using Scala and not using the Dhall interpreter. Now this is a function natural to natural, and this is a wrong Scala tag, and so wrong Scala type, and then we cannot convert. Finally, we do tests also for functions. So we return Scala functions that we then apply to expressions. So this is a function, and then we can use that as a Scala function. So you see, this is a Dhall expression that we say as Scala, natural to natural, and that becomes a Scala function, which we can use in Scala code. And finally, there is a complicated example where we have a natural fold applied to a function type. So we accumulate a function by applying a higher order function several times, and it still works as expected. So this concludes my tutorial in implementing a functional language in Scala.